This is Lab 3, Massive Black Hole by Carter Yunt. The objective of this experiment was to use the position data of a star being pulled towards a black hole to find the mass of that black hole, knowing the mass of the star. Using position and momentum, the force of the star can be found, which can be then used to find the mass. Conditions. The system includes the star. We're going to assume the only force acting on the system is the force of gravity from the black hole acting upon the star. We know the mass of the star is 1.989 times 10 to the 30th kilograms. And we're going to set the time step equal to 86,400 seconds, or the length of one day on Earth. Alright, now for some physics concepts. So we're going to say gravity from the black hole is the only force acting upon the star. So we can say F net is equal to the gravitational force, or the gravitational constant times the mass of the star times the mass of the hole over the radius squared. We rearrange this, we get F net times the radius squared over the gravitational constant times the mass of the star is going to equal the mass of the hole. This equation requires the calculation of F net. So we can say F net is equal to F net perpendicular plus F net parallel. We also know that F net equals dp dt. So we can say dp dt equals dp dt perpendicular plus dp dt parallel, and that P, or momentum, is equal to mass times velocity. So the data we have in regards to the star's position will give us different position vectors. Now we need to calculate F net in order to find the mass of the black hole. So we can find different changes in velocities by taking the positions and subtracting them over the change in time. Then, once we have two velocities, we can take the change in velocity and say that delta P over delta T is equal to m delta V over delta T, because momentum is equal to mass times velocity, to find F net. So, in order to find F net, we can use a computer model to turn location data points into velocity and then into momentum. In order to calculate velocity, we're going to take an index of the data given and say that the change in x is equal to the x value of the index plus 1, meaning the next one, minus the original value, and then say the x velocity at this index is going to be equal to delta x over delta t. We're going to do the same thing in the y position and then move index forward by saying index is equal to index plus 1. Then, in order to calculate momentum and then net force, we're going to use the velocities from before. And we're going to say that momentum initial is going to be equal to the star mass times v initial. From before, we say that v initial is the vector of x velocity of index minus 1 and y velocity of index minus 1. And then p final is equal to star dot m times v final. Obviously, as before, v final equals vector of x velocity index and then y velocity index. Then we're going to say delta v is going to be equal to v final minus v initial, delta p equals p final minus p initial, and then say dp dt is equal to delta p over delta t. As simple as change in momentum is, change in momentum over change in time. F net is going to be equal to dp dt, Newton's second law. And then we're going to say p hat is equal to p initial over the magnitude of p initial. So then we can find d magnitude of p dt is magnitude of p final minus magnitude of p initial over delta t. And then dp dt parallel is equal to d magnitude p dt times p hat. Then we can say f net parallel is equal to dp dt parallel, f net perpendicular, and then dp dt perpendicular is equal to dp dt minus dp dt parallel, since dp dt is equal to dp dt perpendicular plus dp dt parallel, and say f net perpendicular is equal to dp dt perpendicular. Then finally, using the Python code, we're going to calculate the mass of the black hole. We're going to say the distance from the black hole to the star is the square root of x at the index plus 1 times 2 plus y at the index times 2. And so the gravitational constant is 6.67 times 10 to the negative 11th. Then we're going to use the formula before to calculate black hole mass using F net by saying it's equal to the magnitude of F net times the distance times 2 over the gravitational constant times the mass of the star. And here's a little bit of my Python code running. After running the Python code, it output a final mass of the black hole at 2.3371 times 10 to the 31st kilograms. So what does it mean question? The difference between F net and dp dt is that they are a result of one another as opposed to a derived equation. It's a natural law of motion. Although the two are equal, they are not the same. F net is a result of dp dt, or dp dt is a result of F net. You can't derive mathematically one from the other. All right, as for the what if question, if the black hole was replaced and the motion didn't change and there's no other net force acting upon the object, then you could find the mass of the black hole the same way it was done here, or you could just assume that it's the exact same mass as was calculated here. There would be no difference in the final mass if there was no difference in the change of motion.